All right, so now we're going to continue with our next set of pericyclic reactions here. This is called the electrocyclic reactions. So we did cyclo additions last lecture. Those were these Diels-Alder reactions. Electrocyclic reactions are where we're going to lose one pi bond, but gain one sigma bond, okay? So let's see an example here. In terms of how to make sure you draw your arrows correctly. Good news is exact same as the Diels-Alder reaction. You're always going to make sure the base of your arrow is a pi bond and the head of your arrow points to another sp2 hybridized atom. So here we're going to make this jump. Again, the tail of my arrow starts at a pi bond and the head of my arrow starts at an sp2 hybridized carbon. And just like all the other pericyclic reactions, right, there's going to be this circular motion of the electrons that happens in a concerted fashion. That's what makes it this pericyclic. Again, base of the arrow at a pi bond, tip of the arrow at an sp2 hybridized atom. Same thing here, okay? Notice that this jump here is what creates this new sigma bond, right? There wasn't an existing bond here. That's what that jump does, okay? And then the other two are just moving pi bonds around. So this is what moves this pi bond, and this is what moves this pi bond, okay? I guess I can keep my blue one there, just for clarity here. All right, and again, I've lost one pi bond, but I've gained one sigma bond. That's what's going to make these electrocyclic reactions. And this was an example that took place. This is same thing here. So let's just make sure we got this all down, right? Base at the pi bonds, the head at the sp2 hybridized atoms. This one started out with 6 pi electrons, but we can see the same thing that happens with 4 pi electrons. So these are going to be the two main examples that we're going to see. Okay, let's again, where's the base of my arrow going to be? At a pi bond, correct. Tip of my arrow at an sp2 hybridized carbon. Base of my arrow at a pi bond, tip of my arrow at an sp2 hybridized carbon. And so in this case, when you only have 4 pi electrons, what you end up forming is a 4-membered ring instead of a 6-membered ring. Again, I can color code which jump created my new bond, similar to up here. And this jump right here is what moved that pi bond. And again, just because it's this electrocyclic reaction, in both of these examples here, you see that we're losing a pi bond, but gaining a sigma bond. One of the other things is just like those Diels-Alder reactions, you see that these are like ring closing reactions. The only difference is that they're intramolecular as opposed to intermolecular, which is what we saw with the Diels-Alder, right? Here, you're just starting out with one compound that's rearranging itself to form a ring. Notice the way that the equilibria tend to lie, right? So when you're forming a 6-membered ring, it's very much so, I can use a different color, very much so in favor of that product, in favor of product formation. When you're forming a 4-membered ring, it is not. It's actually the equilibrium lies in favor of the reactants. Why might that be? Well, just remember the stability of these cyclobutanes. These 4-membered rings have a lot of angle strain, so they're not particularly favorable to be formed. Okay, doesn't mean that we don't have to learn about them or they're not important, but just note that the equilibrium, this isn't going to be a crazy great reaction in terms of yield. You know, over here you might get a 90% yield, or over here you only get a 20% yield, something like that. Okay. Okay, so this is going to be the hard part of these reactions, is that they can be either catalyzed by heat or light. And depending on which one you use, you're going to get a different stereochemistry of your products, okay? So let's take a look at an example here. Here, we're going to start off with these 6 pi electrons. So they're going to form a 6-membered ring when they close. Now, this one is a little bit different than the other examples because now we have these 2 substituents that are sticking off of my original, this would be a triene, my original alkene here. Okay, so notice that when heat is used to catalyze this reaction, we're going to end up with this cis product. But when we use light to catalyze the reaction, we're going to end up with the trans product. Okay, so depending on what you use to catalyze this reaction, you're going to get something different. And why does that? So why would we even have to worry about stereochemistry? Well, sort of just note when you're looking at your starting compound here, everything here pictured, all these bonds are sort of arranged such that they're all in the same plane, right? But when this new bond forms, right, what's going to happen is this pair of electrons, starting at the pi, ending at the sp2 hybridized carbon. You hear me say it a million times. When this sort of thing happens, well, when this new bond forms, that actually means that, I'm going to erase just for clarity here, we're going to have to twist about these bonds, right, in order to form that new sigma bond, right? That bond, those pi bonds, those double bonds, they don't rotate, but we're breaking one of those double bonds to form a new sigma bond. And in that process, it's going to have to rotate. And so depending on which direction it rotates, you're going to get a different product. So in this case, if they're both rotating in the same way, that would be like if you have the light, so that would end up with the trans product. If they rotate in different directions, that would be like if it was catalyzed by heat, that's how you get the cis product. Okay, so that's why we have this sort of stereochemistry that we have to worry about. I'm going to give you the sort of long explanation as to why this phenomena occurs. And then I'm going to simplify it dramatically at the end, okay? It has this sort of complicated molecular orbital understanding to it, but I figured out a great trick that we can use to just sort of remember 6 electrons, heat will give you this type of product. So bear with me as I go through the complicated one. But then at the end, I'll simplify things dramatically. Let me just say that if we started out with a different stereoisomer of our original product, then that's going to do something different. So for example, if I started out with this one and then used heat, that would get me to the trans product. If I use light, it would get me to the cis product. Okay, so this is going to be the name of the game. You're going to be started with a compound like this, and you're going to have to know what heat does or what light does in terms of the stereochemistry. Also, just note that these reactions are reversible, right? So if light is how you start from this compound here to get to the trans product, starting with that trans product and then hitting it with light would also take you back to that alkene. Okay, so these reactions are reversible. And then when we have the starting out with 4 pi electrons, we sort of see a similar phenomena. If we hit this particular compound with heat, we would actually get the trans product, starting with the 4 pi electron compound. If we hit it with light, then we would get the cis, okay? And so we could sort of play the reverse game as well. If I had started out with a different stereoisomer, then hitting it with light would get me to the trans product, hitting it with heat would get me to the cis product. Okay, so you can see that this can be kind of complicated. So again, I'm going to give you the molecular orbital explanation and then tell you a set of rules that makes it easy to remember which is which, okay? So this sort of just spells out the same thing. I guess important to note, right? When you have the cis product, there's only the one because it's meso. This is chapter 5. There's actually a lecture called meso compounds that you might want to review if you don't know what that is. When you have the trans isomer, then you also have the enantiomer or its mirror image that you also have to consider, okay? So let's go into the long, complicated explanation here, right? So it has everything to do with these molecular orbitals, okay? And again, we're going to have to twist about that existing pi bond. So let's just give, actually, let me take a picture so we can remember what we're talking about here. So this is starting out with this compound here, and these are what the different pi bonds look like in the HOMO, the highest occupied molecular orbital. Remember that there's going to be 2 nodes there, and this is just as if you had the isolated bonds, right? So this would correspond to this pi bond here. This pi bond corresponds to this molecular orbital picture, and this pi bond corresponds to this molecular orbital picture, okay? So then what this image here is as if I imposed that sort of orbitals, the phases of those orbitals on the actual drawing and then tilted it towards me, okay? You see that the outermost p orbitals, this guy here and this guy here, which would be located on this carbon and this carbon, which is where that new bond is going to form, they're in phase with one another. Okay, so that means that when this new bond is going to form, it's going to form either by having this p orbital rotate inward or this p orbital rotate inward, or the reverse, right? Because you have to have your orbitals in phase in order for them to order for them to overlap and form a new bond. Okay, so that's why we see the type of reaction that we do when we hit this thing with heat, is that these guys are currently in phase. They're going to have to rotate inward, and that's how I'm going to get my new orbital overlap, leading to that cis formation. And again, this is, I should have said that at the beginning, this is what happens when it's catalyzed by heat, okay? Is that you start out, I should write this on here as well. This is catalyzed by heat. You start out with your electrons in the HOMO, the highest occupied molecular orbital. The outermost p orbitals are in phase, and so they have to rotate. And what we call this type of rotation, when they have to rotate one clockwise and one counterclockwise, is called disrotatory. Wow, I thought there was only one T. Disrotatory, okay? Meaning that one of them is going to rotate inward, counterclockwise, the other one's going to rotate clockwise. They both have to rotate inwards in order to form that overlap between the orbitals that are of the same phase, okay? When we start out with 4 electrons, and this is again catalyzed by heat. Again, we start out with those electrons in the HOMO when it's catalyzed by heat, that highest occupied molecular orbital. But now, because there are only 4 sets of pi bonds, and this is starting out with something that looks like this, let me make it prettier. Now we only have 4 sets of pi electrons, 4 pi electrons, which means that our outermost lobes are out of phase with one another. Okay, so that means in order to rotate in such a way where like phases are interacting, that means that we have to have one of them rotating. Okay. We're going to have one of them sorry about that. We're going to have one of them rotating inward and the other one rotating in that same direction, right? So both are going to be rotated clockwise in order to form, that would be conrotatory. Okay, and again, the whole name of the game is that they have to rotate in such a way that these like phases interact. And so in this case, you would have the trans product that would be formed with this rotation. Okay, so when you have under these thermal conditions or heat catalyzed reactions, 6 pi electrons would lead to a disrotatory rotation of those outermost pi bonds, and 4 pi electrons would lead to a conrotatory. Okay, so that's why you get these different products, whether you have 6 or 4 electrons. So now, how does that differ then with light? Well, remember what light does is it actually excites an electron from the HOMO to the LUMO, right? To that lowest unoccupied molecular orbital. So now, instead of starting out with a molecular orbital picture that has 2 nodes, we're going to excite it and go to what used to be the LUMO. It's the new HOMO, old LUMO. And that has 3 nodes. And so notice that what that's going to do is change the phase of those outermost orbitals, such that when they were in the ground state, they used to be of like phase, but now in this excited state, they are of unlike phase. Okay, so that means that when we start out with these 6 pi electrons and we catalyze by light, we would lead to a con-rotatory cyclization, whereas if we had started with heat, it would have been the dis-rotatory, right? And again, it's all about those bonds need to turn in such a way that they would have like orbitals overlapping. The phase of those orbitals are of the same. So this is what leads to these two different products, whether or not you catalyze by heat or whether or not you catalyze by light. Okay, so now when we go to the 4 electron situation, we see the same thing because because the absorption of light will excite it to that LUMO. Now that switches the phase of those outermost p orbitals. And so whereas with heat, we had the con-rotatory cyclization, with light, now we have the dis-rotatory cyclization. Okay, so this is this complicated molecular orbital explanation here. You can sort of sum it up here. 4 electrons under thermal conditions would be con-rotatory. 6 electrons under thermal conditions would be dis-rotatory, and then it's reversed when it's catalyzed by light or photochemical. But now again, I told you that I was going to give you this long molecular orbital explanation and then simplify it a little bit, okay? So let's look closely here at what we got here. So first of all, notice that our products can be labeled, of course, as cis or trans, depending on the stereochemistry of those groups relative to the ring. But now let's look at our starting reactants here, okay? And we're going to categorize these in a similar sort of manner. What I'm going to do is I'm going to chop at that pi bond, and I'm going to look at these two groups relative to one another. Notice how they're pointed in opposite directions, okay? We're going to call this trans-like. It's not quite trans because they're not on the same pi bond, but it's kind of got that same idea. We can apply that same logic. They're pointed in opposite directions, so we're going to call that trans-like. Likewise, if we had the opposite stereochemistry, I'm going to do the same thing. I'm going to chop at that bond, and I'm going to notice that now those two groups are pointed in the same direction. We're going to call that cis-like. Okay, so this is this kind of made up stereochemical designation that we've had in order to categorize our starting alkene. Okay, and so what we're going to see is that if we have 6 electrons, 6 pi electrons, like in this case, and we start with the trans-like, hit it with heat, we get cis. Likewise, if we would see that if we started with the cis-like and hit it with heat, you would get the trans product. You can go back a few slides and convince yourself that this is indeed the case. So we have an inversion in our stereochemistry. If we start with trans-like, we get to cis. If we start with cis-like, we get to trans. And note that these are all reversible as well. So if I started with the actual cis closed product, then the reverse reaction catalyzed by heat would also give me that stereochemistry inversion. Same thing down here, right? So we're going to say that using this kind of made up stereochemical classification for our alkenes, these guys over here, we can show that with heat, there would be an inversion in our stereochemistry. Starting with trans-like, you would get the cis, or starting with cis, you would get the trans-like, and vice versa if you started with cis-like, okay? Whereas if we start out with 6 pi electrons, again over here, and we hit it with light, we get no change in our stereochemistry, right? So the trans-like would get us to the trans product, and down here, again, you can go back a few slides and convince yourself of this. Whoops. But if I started out with the cis-like, I would get the cis product. So there's no change that occurs when 6 pi electrons are hit with heat. Okay, I'm sorry, when 6 pi electrons are hit with light. You're not going to get any change in your stereochemistry. And again, the same argument about this being reversible. So if you started out with this trans ring here and hit it with light, you would get to the trans-like alkene. Okay, saying now we can go over here to the 4 pi electron situation, and we're going to do the same thing. We're going to chop it at this bond. We're going to notice that these two groups are pointed on opposite sides. So we're again going to call this trans-like. And we're going to note that if we hit it with heat, that gives us the trans product. Whereas if we hit it with light, it gives us the cis product. Okay, and you can go back a few slides and convince yourself that if we started out with the cis-like 4 pi electron example, we would similarly see no inversion happen when you hit it with heat. So this is no change. Versus when you hit it with light, you get this inversion in your stereochemistry. Okay, so by using this trans-like, cis-like designation, we can dramatically simplify that very complicated molecular orbital picture that I gave you before. Okay, so this is, I think, if your takeaway, what do I really have to remember from this chapter in order to correctly predict products? I think that this is way easier than trying to remember that molecular orbital picture. So hopefully that simplified things for you guys.